in the asteroid belt between Mars and Jupiter, and in a population of space rocks whose orbits bring them close to Earth, there is wealth on a scale that makes the concept of a trillion-dollar economy seem parochial. The asteroid designated 16 Psyche, a metallic body approximately 220 kilometers in diameter orbiting in the main asteroid belt, is estimated to contain iron, nickel, and precious metals in quantities whose total value, if brought to the terrestrial market, would be measured in quadrillions of dollars. The number is so large that economists have noted it cannot be meaningfully converted to present-day market prices, because arriving quantities of precious metals at this scale would collapse the commodity markets they are priced in. 16 Psyche is one object. The asteroid belt contains millions. Near-Earth asteroids, those whose orbits bring them within proximity of Earth, number in the tens of thousands of catalog bodies, and the catalog is far from complete. The space resource economy is not science fiction. It is an engineering problem. The physics is understood. The technology required exists in its component parts. The question is whether the component parts can be assembled at a cost that makes the economics work, with a timeline that survives the financial and political pressures of private or national investment. The geological argument for asteroid mining starts with how metals got where they are on Earth. When Earth was forming approximately 4.5 billion years ago, the planet was largely molten. Heavy elements, iron, nickel, platinum, and the platinum group metals, including iridium, osmium, palladium, rhodium, ruthenium, and others, sank toward the planet's core under gravity. The iron-nickel core of Earth is extraordinarily rich in these elements. The crust, where humans can actually extract things, is relatively depleted. The metallic asteroids, bodies like 16 Psyche, are believed to be the cores of planetesimals, ancient rocky bodies that formed in the early solar system but were shattered in collisions before they could fully differentiate and bury their heavy metals in inaccessible cores. They retain the heavy metal-rich composition that Earth's accessible crust lost when its iron sank to the center. The platinum group metals are of particular economic significance because of their industrial applications. Platinum and palladium are essential to catalytic converters in automotive exhaust systems. Rhodium is used in industrial catalysis. Iridium is used in high-temperature applications. These elements are genuinely scarce in Earth's crust. The total amount of platinum mined in human history would fit comfortably in a large living room, and the demand for them is significant and growing, particularly as clean energy technologies expand. The engineering pathway to asteroid resource extraction requires solving several distinct problems, each formidable on its own. The first is identification and characterization. Not all near-Earth asteroids are equally valuable or equally accessible. The most attractive targets are metallic or carbonaceous bodies whose orbits bring them close enough to Earth that the energy cost of reaching them is manageable, and whose composition makes the extraction economics work. Telescopic observation can identify asteroid types and approximate compositions from their reflective spectra. The next generation of space telescope infrastructure will dramatically improve the completeness and accuracy of the near-Earth asteroid catalog, identifying high-priority targets more precisely. The second is transportation. Getting to an asteroid and getting extracted material back to a useful orbit or to Earth requires spacecraft. The energy costs of different trajectories, expressed in terms of a quantity called delta V, the change in velocity required, vary enormously depending on the target's orbit. Some near-Earth asteroids are actually easier to reach, in energy terms, than the surface of the Moon. Others require more energy to reach than Mars. Mission design for asteroid resource extraction requires careful selection of targets that balance composition, size, and orbital accessibility. Returning material to Earth in bulk quantities presents its own challenge. Bringing metallic or from an asteroid directly to Earth's surface would require either controlled deceleration using enormous amounts of propellant or aerobraking through the atmosphere, which works for small capsules but becomes increasingly difficult at larger scales. The most commonly proposed solution is to return extracted material not to Earth's surface, but a high Earth orbit or a Lagrange point, where it can be processed into useful forms, refined metals, water for propellant, structural components that can either be used in space or deorbited in smaller quantities. The third problem is extraction. No one has yet developed and demonstrated asteroid mining technology in space. The concepts that have been studied include robotic surface mining, using techniques adapted from terrestrial open-pit mining, capturing entire small asteroids and enclosing them for processing, and volatile extraction from carbonaceous asteroids, which can contain water ice, ammonia, and carbon compounds that are enormously valuable as in-space resources. Water can be split into hydrogen and oxygen for rocket propellant, transforming an asteroid into a fuel depot in space. The economics of asteroid mining are the critical uncertainty, and they are genuinely complex to evaluate. The cost of sending spacecraft to asteroids and returning material has been dramatically reduced by the development of reusable launch vehicles, SpaceX's Falcon 9, and the under-development Starship system. But space operations at the scale required for economically meaningful resource extraction remain expensive by terrestrial industry standards. A mission architecture capable of returning thousands of tons of material annually would require capital investment comparable to major terrestrial mining projects, with the additional complexity of operating in deep space with no ability to send a repair technician. The market side is equally complex. The platinum group metals extracted from asteroids will be worth enormous sums at present terrestrial market prices, but those prices reflect scarcity. If asteroid mining succeeded in dramatically increasing supply, prices would fall, potentially undermining the economics that made the project viable in the first place. This is not a hypothetical concern. It has happened in terrestrial mining repeatedly when new large deposits were opened. The more robust economic case, made by researchers and entrepreneurs in the field, focuses not on bringing asteroid resources to Earth's surface markets, but on using them in space. The most expensive component of any space operation is lifting mass out of Earth's gravity well. An asteroid that provides propellant, shielding material, and structural metals in orbit eliminates this cost for subsequent operations. As the space economy expands, through satellite operations, space tourism, potential lunar or Martian development, the value of in-space resources decouples from the distortions that would affect terrestrial commodity markets. NASA's mission to 16 Psyche, launched in October 2023, represents the first dedicated investigation of a metallic asteroid. The spacecraft, designed to orbit Psyche for approximately 26 months beginning in 2029, will conduct the most detailed characterization of a metallic asteroid body ever performed, providing data critical to understanding the composition, structure, and potential resource content of bodies like it. Private companies including Planetary Resources and Deep Space Industries, both of which have since been acquired or wound down, made early attempts to develop asteroid mining technology. The current landscape of private space resource development is more diverse, including companies approaching the problem through lunar resource extraction, propellant production, and in-space manufacturing. The legal framework for space resource extraction has evolved to accommodate commercial development. The United States Commercial Space Launch Competitiveness Act of 2015 established that American citizens and companies have the right to own resources extracted from space, even though space itself cannot be claimed as sovereign territory. Several other countries have enacted similar legislation. The Artemis Accords, signed by a growing number of nations, include provisions related to space resource utilization. The asteroid mining proposition rests on a simple, physical reality. The solar system contains vastly more of everything that industrial civilization needs than the Earth's accessible crust can provide. The constraints that govern terrestrial resource economics, scarcity of high-grade or deposits, the environmental cost of extraction, the geopolitical concentration of specific critical materials in specific countries, are Earth-specific. They do not describe the broader reality of material abundance in the solar neighborhood. Whether humanity develops the capability to access that abundance before terrestrial resource constraints become critically binding is the question. The engineering challenges are real. They are not by the assessment of the engineers and scientists who study them seriously, beyond the reach of technologies that exist or are in development. The quadrillions are out there. The question is whether we go and get them.